Let's look now at some non-obvious examples. Let's start with characteristic polynomials with imaginary roots. So this ODE seems tame enough. Y second plus y prime plus y equals to 0. And the characteristic polynomial also doesn't look that weird, but if you start computing, you figure out that it has imaginary roots. And at first, I'll just behave as that doesn't bother me at all. I'll just keep on going as I did in the first two examples. I'm just gonna write the two partial solutions, and I'm just gonna write the general solution as the sum of the two partial solutions. And now I'd like to see if the fact that I have imaginary roots is bothering me further, because what I expect y to be is a real solution, not an imaginary one. How can I get rid of the imaginary term? Well, first of all, I'm gonna take out of a parenthesis the part of the exponential that doesn't deal with the imaginary number, so I can concentrate on the part that has the imaginary number in it. And I remember the Euler formula. This is a very important mathematical formula, but I don't really know if you have been using it before. So it's a way to relate the imaginary powers of the exponential to the trigonometric functions, cosine and sine. It's extremely useful, but this might be one of the first applications you have seen. So I just apply the Euler formula, and I transform all my exponentials of imaginary numbers in cosines and sines of things that are not imaginary anymore. On the other side, I have now the imaginary number in front of the sign, so it hasn't disappeared just yet. And here I remember that cos of A is equal to cos of minus A. It's an even function, and sine is an odd function. Sine of A is equal to minus sine of minus A. With these properties of sine and cosine, I can match the sine of square root of 3 over 2x with the cosine of minus square root of 3 over 2x, and so I can do with the sine, thus simplifying the equation I'm looking at a little bit. And now I have the imaginary number in just one position. That's great. Not ideal yet, it's still there. I want to get rid of it. And I'm just going to get rid of it by saying that I want C1 and plus C2 to be real, and the imaginary number multiplied by C2 minus C1 to be real as well. We also expect, because it's a second order equation, that we have to satisfy two initial conditions, or boundary conditions. So we still want two levels of flexibility in our final solution. As we solve it is by deducing from these constraints that C1 and C2 need to be complex. They also need to satisfy that their sum is real and their difference times the imaginary number is also real. If you do the math, if you do the computations on the side, well, what you can do is just saying that the sum of C1 and C2 is a new variable A, and their difference times the imaginary number is a new variable that we will call B. The number of degrees of freedom, if you're comfortable with this notation, hasn't changed. So we still have enough information. So we can go from this ODE through the imaginary roots to a solution. Here there is a mistake, I should not be there anymore, but we have fully constructed the solution. And we say it's an oscillatory solution for the obvious reason that it oscillates over x, because it has a cosine and a sine. Let's look at a new example, an example with repeated roots. So it's another example of a second order linear homogeneous equation. We construct the characteristic polynomial, and this characteristic polynomial has only one root, minus 1. It's just repeated twice algebraically. So if we follow what we have been doing before, we say that there is only one partial solution, e at the minus x, but we still need to satisfy two boundary conditions while having only one unknown, so this is a bit sketchy. But we have already seen the idea of variations of parameters. So instead of looking at a being just a constant, we're now introducing a being a function of x itself. And we try to match our new unknown, so a of x, e at the minus x, into our ODE that we have been looking at. So how we do that, as we have done a couple of times already, we take the various derivatives of y prime has a prime appearing and minus a of x. Y second, we just keep going. There is always the exponential of minus x everywhere, so we can simplify that. But y second will have a double prime appearing minus 2a prime plus a. We can plug this first and second derivative inside our ODE and drag e to the minus x out of it. Well, now we have something that, by the way, simplifies a lot. We end up having only the leading coefficient, the leading term, the one with the highest derivatives, staying in our equation. We also know that e to the minus x is non-zero. So we got to the equation that a double prime is equal to 0. This is only satisfied by linear polynomials of degree 1. So we can write a of x as a polynomial of degree 1 that has two unknowns, c0 and c1. And this is our final solution. As a general rule, if lambda is a root of order n of the characteristic polynomial, its contribution to the solution is a polynomial of order n in x times e to the lambda x.